see the streamers, the cirrus, which is associated with the great dark spot at this particular latitude. You can also see that there's a cirrus streamer up in the northern hemisphere. Your eye begins to pick up some patterns with this kind of a presentation that aren't necessarily so obvious when you sit and stare at the images one at a time. And of course, once we can actually make this into a time-lapse movie where the atmosphere is actually moving, and we have that data, it will really be a very valuable tool as well as a very beautiful thing to look at. Okay, I think Brad Smith's up next.
Good morning. We found ourselves this morning in the position of trying to analyze the images that came in yesterday afternoon and last evening so that we would have something to say about them this morning, while at the same time being terribly distracted by extremely high resolution images that kept showing on the screens and diverting our attention. We are getting very, very close to the planet now, and almost every imaging frame that comes back is extremely exciting. I have a number of slides I would like to show this morning, so I think it's best just to get right into them. And the first is a very high resolution image taken of the great dark spot. Again, this was all possible courtesy of Andy Ingersoll and his group of forecasters, who really did an outstanding job on the great dark spot and allowed us to put the images exactly where they should go. You can see a lot of structure now in this image. A lot of structure in the high cirrus type clouds, but still not much down in the spot itself, and that may take more detailed processing than we've been able to do at the moment to bring out any structure that might be down in there. This is the highest resolution image now that the narrow angle camera will take of the great dark spot. It's over near the limb. The very, very smallest clouds that you see in this image are only 25 kilometers across. And this image, I believe, was shuttered only about 20 hours before closest approach. So this is the highest resolution image. You can see the limb of the planet up here. It's quite foreshortened because it was close to the limb. And it's just showing that all of these clouds are breaking down into very, very fine structure. That essentially is the message in this image, which has now been map projected to bring out some of that structure. And it's making it extremely difficult for the dynamicists. The dynamicists are trying to track these individual clouds, to look at a particular cloud and then see where it is a few hours or maybe 10, 18 hours later, and having difficulty locating them, because what we're seeing here are not clouds that are rapidly moving. The air around them is rapidly moving. This is in a very high velocity region. There are undoubtedly very strong shears. But these can be considered analogous to the lenticular clouds that you will see hanging over mountains. They seem to be just stationary over a mountain, but the air that's going through them is going quite rapidly. And what's happening is that as the winds blow through this region, they get deflected upward. Now, whether that is due to the great dark spot itself, we don't know that, but it quite probably is, that there's something about that dark spot that deflects these winds upward as they go up, carrying volatiles like methane in them. They reach an altitude where those volatiles condense out and form clouds. Then as the wind moves on, it descends and it goes down into a warmer region, and these little ice crystals of methane sublimate, they disappear, evaporate. And so the cloud appears to be stationary, even though the winds are moving very, very rapidly through this region. The next slide illustrates the problem. Again, these are map projected, but these images are only 2¼ hours apart, and yet you can see there are some major changes that have taken place in only 2¼ hours. This cloud right here, for example, which isn't even seen in this image. Is it this that's moved to here, or is it just this one is faded out and a brand new cloud has been created in its place? And those are the kinds of problems that we're having, and it's the reason that we're a little bit slow this time in getting actual velocities from the cloud motions. This is now a high-resolution image of the smaller dark spot, the one that's been called E2. Those of you who were around early this morning may have seen an extremely high-resolution image of that cloud filling the field of view of the narrow-angle camera. We'd like to say we predicted that, but I have to be honest, it just by chance happened to fall right into the center of one of the frames that was taken while the infrared instrument was scanning up and down on the planet. But it's an absolutely magnificent photograph, and should have a processed version of that available for you tomorrow. What this is showing is what we suspected, that the bright cloud in the middle of this dark feature is high. It's convection. It's moving upward. This is a false color image where we use ultraviolet as an additional color, and in general, whatever looks very blue is deep, and what looks somewhat pinkish color here is high. So it's just a demonstration of height for the particular clouds in the center of that dark spot. There are other ways of getting height. This is a false color image which has been generated using the wide-angle camera. It's an orange frame and a short wavelength methane filter and a longer wavelength methane filter, all together to produce false color. Normally, these images are analyzed not by creating an image, but by studying the numerical values that come out of such an image. But it does provide some graphical evidence of height. And in this particular image, if anything that's white is very high, and what's perhaps pinkish is intermediate in height. And you see it has a sort of a orangish brightening around the limb. The reason for that is that material near the limb is reflecting light before it has a chance to be absorbed by methane. And the reason for that is that there's just very, very long path lengths through the atmosphere near the limb, and the probability that it would reflect a grain of ice and bounce back up is much higher near the limb. Well, there are other ways of measuring height, and this image appeared to us yesterday afternoon, and what we are actually seeing are cloud shadows. These are some of the very high cirrus-type clouds, and you can see right along the edge of each one is what is almost certainly a shadow caused by these clouds. Now, this, to the best of my knowledge, is the first time that Voyager has actually been able to show or see cloud shadows on any of the planets that we've looked at. So this was quite a surprise for us, and quite a pleasant surprise, because it allows us to make some estimates of the heights of these clouds. And I guess we've got a bad slide up there somewhere. Yeah. Okay, maybe you can just kind of push it down in there. Okay, this shows about where those clouds are. They were down in the South Polar region. This is the South Pole, and the sun is shining in this direction and casting shadows along the southern margin of the clouds. Well, by looking at these images, it's possible to make some estimates of height, because we know exactly what angle the sun is shining at, and we can measure projected distance of the cloud to the shadow, and that gives us a measure of how far it is from the cloud down to this more or less uniform haze layer or lower cloud level upon which the shadows are cast. The measurements so far are really quite preliminary, but the number turns out to be quite extraordinary, something of the order of 50 kilometers between these very high clouds, these cirrus-type clouds that we've been talking about, 50 kilometers from there down to this lower cloud deck. And there were some estimates from the team this morning that they could be as high as 75 kilometers. And here is just another view of a different part of the planet, but again showing some of these little high puffy clouds casting shadows on the lower cloud deck. Well, turning from here to the rings, I have, okay, we need to push that one down too, if you would. It's a better piece of artwork, what I had showed you yesterday, trying to show the relationship between the more or less continuous ring, the outer ring, which is composed of several fairly bright segments, and then a longer and more diffuse region. And as of yesterday, I believe this was the region within which we had not seen any ring material at all. But we did take wide-angle frames last night, and I'll show you one in just a moment, in which we have now seen material extending further along here and further along here, and now there's only about 10% of the ring in which we have to date been unable to see anything. So I think that it's almost certain now that this is a complete ring, and that the amount of material over here is just so very, very thin that over a certain range anyway, about 30 degrees or so, cameras have not yet been able to record any material in there, but certainly it has to be there. This is 1979, 1989 N3 and 1989 N4. This now is one of the images that was recorded this morning. Here again, I mentioned yesterday, there are artifacts that appear around bright objects in the field of view. This is 1989 N2. This trailed out because of its orbital motion. This is a star, and here you can see the outer ring. Now this is the trailing edge, fairly sharp, but with material which extends on, and this is the leading edge, getting more and more diffuse as you go along, and here is the inner ring curving around like so. And as had been suggested in some of the images that we took, that we acquired over the past few days, this ring also seems to show some structure. Certainly not nearly as varied as the outer ring, but it's not perfectly uniform as we go around. We have two new satellites, and here they are. This is the planet, 1989 N5 and 1989 N6, and out here 1989 N3. And you can see quite easily just from these photographs that N5 is quite a bit fainter than N3, and N6 is even fainter than N5. And if I can have the first view graph, this will now give you a listing of the satellites as we understand them right now. So this is the temporary name. Eventually this IAU committee will put formal names on these objects, but that won't happen until later this year. The orbital radius, the distance from the center of the planet now. The orbital period expressed in hours. The orbital inclination, that is the angle between the plane of the satellite and the planet's equatorial plane. For almost all of them, a value very, very close to 0, but this last one showing an appreciable inclination certainly a measurable inclination of roughly 4.5 degrees. It certainly shouldn't be taken as 4.5. We just didn't have a little half sign to put in there on the machine that set up the graph. But 4.5 degrees, probably plus or minus a half degree, so that needs to be pinned down further. And here are the estimated diameters of these objects. Now, they have not been resolved. The smaller ones certainly have not been resolved. And so what we did was just to assume, and I think it's a reasonable assumption, that they all have roughly the same reflectivity. And so by measuring their brightness, that gives us an estimate of what their diameters are. So we go from 89, I keep saying that, 89 N1 up around 420 kilometers in diameter, all the way down to the most recent two, which are about 90 and 50 kilometers respectively. And I will make copies of this, or the Public Information Office will make copies of this so that you can pick them up afterwards if you like. Well, we can have the view graph off now. These are a couple of images of N1. We're actually beginning to resolve it. I'm showing you two of them to show that the shape is not due to some peculiar properties of the Vidicon or due to image smear. It is really out of round, and it's probably getting up to about the largest satellites that you can imagine that won't pull themselves into a spherical shape. And if you were going to try to draw some conclusions, what does all this mean? One conclusion that you might draw is that this object, because it is out of round, has remained rigid since its formation. Now, we don't know when it formed, but had it partially melted, it probably would have pulled itself into a more spherical shape. So it's probably reasonably pristine since its formation, whenever that was. This summarizes, in the slides that follow, summarize some of what we know right now about Nereid and 1989 N1 in comparison. You'll notice that if our estimates are correct here, Nereid is not the second largest satellite in the Neptune system, but it is instead 1989 N1. The albedos are similar. Nereid is around the 10% level, 10% reflectivity, whereas N1 is very dark, reflecting only about 6% of the light that falls on it. There have been questions over the past few days, does Nereid vary in brightness? There were ground-based observations made a year or so ago which suggested that its brightness varied over something like a magnitude and a half, which is a factor of 3 or so in brightness, and that is not observed. The brightness amplitude variations are less than 10%. I don't know exactly what the number is for N1 right at the moment, and neither did the person who put the slide together, but it's apparently a small variation. We don't know what the period of Nereid is, but we would be surprised if it was synchronous. That is, the inner satellites are more likely to keep always the same face toward Neptune. Triton does this, but Nereid is in this very peculiar orbit that takes it way out from Neptune, and it would be surprising if it did always keep the same face toward Neptune. Almost certainly N1 does, and so we show a estimated rotation period for it being about the same as its orbital period. Notice that Nereid has this very long orbital period about Neptune, approximately 1 year. Now, these are some of the geometric albedo, essentially reflectivity measurements that have been made as a function of wavelength for Nereid, all running somewhere up around 10 or 12% here, and no trend with wavelength. That is, this would be blue or violet in here. This would be, well, sort of a blue-green, let's say, and this would be out in the green region. And so it's fairly neutral. And this is consistent with this darkish material that we see in the outer solar system. It is dark, and quite neutral in its color. That is, it tends to be a dark gray color. We don't yet have color on 89N1, but you can see, shown here, that it is definitely darker than Nereid. And just one more slide showing how Nereid gets fainter with increasing phase angle, the phase angle being the angle between the sun and the observer as seen at the object in question, in this case Nereid. What this does illustrate, it's just further illustration that this satellite is not varying in brightness, because these are taken at different times, but they fall along a fairly nice straight line, whereas the ground-based observations that had suggested light variation would have had it ranging from the top to the bottom of the screen up here. This now is our fairly recent false color image of Triton. False color in that we have used ultraviolet for the short wavelength, violet for the intermediate, and green for the longer wavelength. And the purpose of the false color is to show what tends to be bluish or whitish, and you can see along these margins of along the dark areas, the reddish areas, this blue color which is persisting. This little region in here, for reasons we don't fully understand, is darker in ultraviolet. That makes it show up somewhat more orange in this particular image. And you can see the detail beginning to just become finer and finer. This image is, I think, our most recent image now of Triton. And it's taken through a violet filter, and we've put a map grid over it so you can see just about where the South Pole is. This is the equator up here, so the equator is running sort of along like so, and the terminator is along over here. And again, finer and finer detail. There are some members of the imaging team who believe that they are seeing craters, but they certainly haven't convinced me of that yet. But again, we don't have to wait very long before we really know. And then this is the color image which goes with the violet that I just showed you. And again, one can see the reddish color of the darker areas up around the equator, and the overall pinkish color of the bright regions, which, as we've said a number of times now, we believe is due to chemical processing of the volatiles, the methane and others perhaps, due to high energy particles. The final view graph, I guess, we can have that up here now. I've just will indicate for you when some of these high resolution images will be getting down on the ground for these new satellites and Nereid. So we will have some fairly good images of 1989 N1, 4 of them coming down Thursday about noontime tomorrow. And sorry, today? Oh, right. Okay. Well, it's a shorter wait than I thought, okay. I'm glad you told me it was Thursday. I thought it was still Wednesday. Okay. Nereid coming in this afternoon. This will be the very highest resolution images of Nereid. And I warn you, don't have great expectations, because Nereid was just way, way out in its orbit at the time these images were taken, and they aren't very many pixels across. The highest resolution images of N2 will be coming in this evening, 3 images. Then the very highest resolution image of N1 will also come in this evening, but I put down that it's a partial image, and that is that before the whole thing gets played out, the window goes away and the tape recorder has to stop running. And so, I don't know, maybe it'll be 2/3 of a frame. We're not exactly sure, but not to worry, because those who want to hang around until the early hours of tomorrow morning, we'll replay it and get the entire image down. So this is the schedule. This is the time that they should appear on the monitors. That's all I have, but we can make copies of this available also to you afterwards.